Hello. In this video, I'm going to present the chain rule for functions of several variables. Like a lot of the things that we do in this class, this is an extension of or generalization of something from Calc 1 to functions of several variables. And extending it to more than one variable makes it more difficult and also more interesting. So I'll give you a quick review of the regular chain rule in one variable. Now, we have two notations for the chain rule, the functional notation and the dy dx notation. I think it's the Leibniz notation. In this class, the less confusing notation to use is the Leibniz notation. So I'll go over the Calc 1 chain rule with that notation. Now the chain rule says that if y is a function of u, and u is a function of x, then dy dx equals dy du times du dx. Now, you need some assumptions, like you need to assume that those derivatives exist in the first place, and you can find them in any calculus textbook. So I'm going to draw a diagram showing the variables, which you don't really need in Calc 1, but diagrams like this will be useful for us. So x is called the independent variable. Y is the dependent variable. And u is the intermediate variable. I'm not going to test you on this, but it's worth thinking about. Now, y depends on u. X doesn't depend on anything. U is in between because on one hand, u depends on x, but on the other hand, y depends on u. Now, what we're going to do today is similar situations where there could be more than one independent variable. There could be more than one intermediate variable or both. And we'll find derivatives of y with respect to the independent variable or variables in terms of derivatives between directly connected variables. And for every number of intermediate variables and independent variables, we get a different chain rule. And the best way to find them is not to memorize all of them, but to construct them by drawing a tree like this. So I'll show you a couple of these chain rules, and you should get the pattern and be able to do it for any number of variables. Okay. So the simplest case is probably if we have two intermediate variables and one independent variable. I'm going to draw the tree diagram first, but not with a highlighter. So suppose z is a function of x and y are functions of t. Then we can think of z as a function of t. And if things are smooth enough, then dz dt exists. That's the partial derivative of z with respect to x times dx dt plus del z del y dy dt. And we write down the chain rule. So suppose z is a function of x and y, and x and y are functions of t. And also assume that enough derivatives exist. And if you look, you can look it up somewhere and find the exact assumptions, but we don't need to go there. Now, one thing that might look a little weird about this is the right-hand side has both partial and regular derivatives. That's because z is a function of x and y. But x and y are each a function of only one variable. So those are regular derivatives. Don't sweat that too much. It's confusing. So if you write the wrong kind of derivative there, it's not a big deal. Another thing that makes this confusing is if you look at the regular Calc 1 chain rule, you can pretend that everything there is a fraction. And then on the right, the du's cancel and it acts just like a fraction. You can't do that anymore. If I pretended that all these things that look like fractions are fractions, and I canceled out the del x and the dx and the del y and the dy, I'd get 2 dz dt, not dz dt. So that doesn't work anymore. Now, the way I wrote down this diagram is I looked at all the paths I could take from z down to t. There's 2 of them. And for each path, I take the derivatives between each pair of variables and multiply them and add them together. And we'll do that for the more complicated chain rules also. So here's an example of using it, but not with the highlighter. So let's let z equal x over y, x equals e to the 3t, y equals e to the 5t. I'll find dz dt both with and without the chain rule. Now, it's a lot easier to do it without the chain rule. I'll be honest with you. But problems like this are a good way to learn how to use the chain rule, because once in a while you actually do need the chain rule. Well, let's do it without first, because that's easier. To do it without, we just write z in terms of t. So z is e to the 3t over e to the 5t. It's e to the minus 2t. And dz dt is minus 2e to the minus 2t. Okay, now let's do it with the chain rule, and we should get the same thing, of course. So del z del x, z is 1 over y Del x del t is 3e to the 2t. To find dz dy, I'm not going to use the chain rule. I mean the quotient rule. Instead, I'll write z as x y to the minus 1. So del z del y is negative xy to the minus 2. And dy dt is 5e to the 2t. Yeah, not 5e to the 5t. Now, I should write this in terms of t alone. So I'll replace every y with e to the 5t and every x with e to the 3t. Y squared is, oops, I forgot to replace the x. Y squared is e to the 10t, 5e to the 5t. This simplifies as 3e to the minus 2t minus 5. The 5 plus 3 minus 10 is negative 2. And I get negative 2e to the minus 2t. So the same answer as before, fortunately. Okay. So this is probably the simplest chain rule. Well, let's pump up the volume a little bit and use the 2 intermediate and 2 independent variables. I'll call this chain rule 2. There's not really an official numbering of them. So suppose z is a function of x and y, and x and y are functions of s and t. Then we can think of z as a function of s and t, so it should have partial derivatives. Del z del s and del z del t. All right, and to figure out what the formula, I'll draw the tree diagram again. So the dependent variable is z, the intermediate variables are x and y, and the independent variables are s and t. Now, I forgot to write that on the previous chain rule. So z is the dependent variable. X and y are the intermediate variables. And t is the independent variable. Here, z is the dependent variable. It depends on everything else. S and t are the independent variables. And x and y are the intermediate variables. Now to find del z del s, what I do is I start at the top of the tree at z and look at all the ways I can go down to s. And there are 2 such paths. Along each path, I take the derivatives between the variables, multiply them, and then I add those products. So del z del s is, oops. Del z del x del s plus del z del y del s Now, all of those are partial derivatives because x and y are functions of more than one variable and z is a function of more than one variable. For del z del t, I do something similar. Okay, on the tree diagram, I go from z down to t in all the possible ways, and there's two of them. For each path, I take the derivatives between adjacent variables, multiply them, and add the products. So that'll give me del z del x, del x del t, plus del z del y del t. Now, in our textbook, they draw the tree diagram in a different way, so it doesn't really look like a tree. It might look like a diamond. This is the way that our previous textbook does it, and I prefer this way. I think it's more popular also. So let's do an example. So let's let z equal, say, xy squared, x equals, oops, st cubed, y equals s over t. And let's find del z del t. And I'll use the chain rule. You could do it directly, I mean, without the chain rule. It would probably be easier. Okay. So I'm going to use the bottom chain rule. So first thing I would do is draw the tree diagram, and then I use the tree diagram to write the chain rule. Now, del z del x is, let's see, y squared. Del x del t is 3st squared. Del z del y is 2xy. And for dy dt, again, I'm not going to use the chain rule because you don't need it. I'll rewrite y as st to the minus 1. So del y del t is minus st to the minus 2. Now I want an answer that's in terms of s and t, and I always do that on exams and on homework. If the book doesn't tell you to, I add that instruction. So I'll replace every y with s over t and every s with every s with st cubed. That gives me s over t squared times 3st squared plus 2st cubed s over t times negative s over t squared. That simplifies to, let's see, 3. Well, the t's cancel, so you get 3s cubed. And the t's also cancel in the second chunk. See, when I wrote this example months ago, I planned this. It didn't just happen like this. So you get 2s cubed. So that's plus 2s cubed. And that simplifies to 5s cubed. Okay. Now I paused the video and I just restarted it because this answer is wrong. It doesn't look right and it's not right. Because if this were the answer, this is del z del t. If that were correct, then the original function would be 5s cubed t. And if I wrote this in terms of s and t, I would not get 5s cubed t. But I found out my mistake. I missed that minus sign right there. So that plus should be a minus. Okay, so that plus should be a minus. And our final answer is s cubed. Okay, sorry about that. And if I had done this problem without the chain rule, then z would have been s cubed t, and del z del t would work out to be s cubed. So let's do one more chain rule. Let's take 3 intermediate variables and 1 independent variable. So suppose I need to use a different letter, don't I? Okay, so suppose u is a function of x, y, and z. And x, y, and z are functions of t. Then we can think of u as a function of t. So du dt should exist, provided everything else is differentiable. And to write down that chain rule, I'll draw the tree diagram. So the dependent variable is u, intermediate variables are x, y, and z, and the independent variable is t. And to find du dt, I take all the paths from u to t, multiply the partial derivatives along each path, and then add those products. That gives me del u del x dx dt plus del u del y dy dt plus del u del z dz dt. And again, this looks weird again, because on the right-hand side, we have both partial derivatives and regular derivatives. That's because u is a function of 3 variables, but x, y, and z are each a function of only 1 variable. So let's do an example. So suppose u equals xyz squared, x equals t squared, y equals e to the 2t, z equals cosine t. Let's find du dt. Now this is a problem where the chain rule might actually be useful, because if I tried to do it without the chain rule, I would write u as a product of those 3 fellas, and I would have to take the derivative of a product of 3 different kinds of functions. And that is, if you've never done that before, you might get stuck and not know what to do. But you can do it using the chain rule. So after drawing the tree and writing the chain rule, I have du dx is yz squared. Dx dt is 2t. Del u del y is xz squared. Dy dt is 2e to the 2t. Xy is t squared e to the 2t. Oh, I'm sorry, I forgot the del u del z. Del u del z is 2xyz. dz dt is minus sine t. Now I want an answer that's in terms of t alone. So I'll replace all the x's with t squared, all the y's with e to the 2t, and all the z's with cosine t. And when I do that, I'll get e to the 2t cosine squared t plus 2t squared cosine squared t e to the 2t minus 2 t squared e to the 2t sine t cosine t. Now you can leave it like that, you know, on an exam. These answers tend to be long, but I'll try to tidy it up a little bit. I can factor out the e to the 2t, and what's left over is 2t squared cosine squared t plus cosine squared t minus 2t squared sine t cosine t. No, that's right. You could factor out a cosine t if you really wanted to, but it's not a big deal. That's the final answer. So this is about all that I'm going to insist you do on quizzes or exams for this in fall of 2020 on the chain rule. And next time we'll do something different. So I'll see you in class.